The valley floor vibrates. It isn't an earthquake. It is the resonance of 5 million liters of water, hitting the bedrock every single second. The sound is deafening. A continuous, thundering roar that drowns out thought, shaking the fillings in your teeth. But the danger isn't the noise. It is what is happening 30 meters beneath the frothing, white water surface of the plunge pool. There, invisible to the engineer standing confidently on the crest, the solid granite foundation is being eaten alive. The river isn't flowing over the dam. It is actively digging a grave for it. Suddenly, the angle of the spillway shifts. Just a fraction of a degree. A hairline fracture screams across the concrete face, louder than the water itself, tearing through the rebar like cotton thread. The toe of the dam, the massive concrete foot that anchors the structure to the earth, finds itself resting on nothing but air. The support is gone. Gravity takes the wheel. The entire monolith, weighing 6 million tons, begins to rotate forward. The reservoir behind it, a sleeping giant of potential energy, wakes up and pushes. The concrete disintegrates. A wall of water vaporizes the forest instantly. Let's find out. Most turn away. But here at Surphysia, we decode the math behind the chaos. Support the mission by subscribing now. To understand why a mountain of concrete can be brought to its knees, by the very water it is meant to control. We have to look away from the towering wall and look down into the darkness of the impact zone. This is the story of scouring, the silent predator of hydraulic engineering. It is a phenomenon that operates on a timescale that tricks the human mind. We see a dam standing firm for 50 years, and assume it is eternal. But geology operates on a different clock. And high-velocity water accelerates that clock, from millennia to minutes. Consider the energy profile of a large hydroelectric dam. You have a reservoir holding back billions of cubic meters of water. This is potential energy. Static and waiting. When the spillway gates open, that potential energy is instantaneously converted into kinetic energy. By the time that water travels down the smooth concrete chute of the spillway, it is accelerating to speeds topping 150 kilometers per hour. This is no longer a liquid. It is a projectile. It is a coherent beam of mass, possessing a momentum so high, that when it strikes the stationary bedrock at the bottom, the energy release is equivalent to a continuous detonation of conventional explosives. We call this area the plunge pool. It sounds like a leisurely swimming spot. But physically, it is a chaotic reactor of fluid dynamics. When that jet of water strikes the riverbed, it doesn't just splash. It drills. This is the mechanism of scouring. It is the localized excavation of material by fluid flow. It creates a hole that grows deeper, wider, and most critically, backwards, towards the dam itself. Imagine you are standing on the edge of a sandy beach cliff. You take a high-pressure fire hose, and aim it at the sand directly at your feet. What happens? The water blasts the sand away, creating a pit. As the pit gets deeper, the edge you are standing on becomes an overhang. Eventually, the structural integrity of the cliff edge fails, and you fall into the hole you created. Now, replace the sand with basalt or granite. Replace the fire hose with a jet stream carrying the weight of a freight train every second. And replace yourself with a 300-meter tall concrete wall. That is the peril of scouring. The physics of this destruction begins with the concept of the hydraulic jump and energy dissipation. Ideally, engineers design a stilling basin at the bottom of a dam. A concrete apron meant to take the beating. They install concrete blocks, called baffle blocks, which act like teeth to break the water's speed. But nature is rarely contained by geometry. During a flood event, or simply over decades of operation, the water may overshoot this protective apron. It hits the natural rock beyond, Let's slow down time. And look at the exact moment the water jet impacts the rock. We are talking about pressure fluctuations that are incredibly violent. The average pressure might be manageable. But in turbulent flow, we deal with macroturbulence. These are massive, swirling vortices of water that create pressure spikes lasting only milliseconds. These spikes can reach pressures of 60 bar. To visualize 60 bar, imagine the pressure of the ocean at a depth of 600 meters. Or the weight of a main battle tank concentrated onto a dinner plate. This pressure hammers the rock floor. Not once, but continuously, vibrating the geological strata. Under this relentless pounding, the bedrock begins to fail. It doesn't melt. It fractures. Water is incompressible. When a high-velocity jet hits a tiny crack in the rock, a fissure no wider than a sheet of paper, the water is forced into that crack at supersonic speeds. This is known as hydraulic jacking. The water acts like a wedge, driven by the immense weight of the column above it. It pushes the rock layers apart. It creates internal pressure within the rock mass itself. Then comes the uplift. As the turbulent water swirls over the surface, it creates zones of low pressure. A vacuum effect, similar to the lift on an airplane wing, but violent and erratic. This suction pulls at the fractured blocks of stone. A slab of granite weighing 10 tons is lifted out of its geological bed, as if it were a pebble. Once it is lifted, the current catches it. Now, you have a 10-ton boulder caught in a whirlpool of water, moving at 40 meters per second. This boulder becomes a weapon. This is the ball mill effect. The boulder is dragged around the bottom of the scour hole, grinding against the bedrock like a pestle in a mortar. It pulverizes the stone beneath it, deepening the hole further. The noise of this grinding, if you could hear it over the roar of the water, would sound like the earth itself is screaming. It is the sound of geology being dismantled. This abrasive process accelerates the excavation. The hole gets deeper. 5 meters. 10 meters. 20 meters. In some major dams, scour holes have been measured to depths exceeding 80 meters. That is a hole deep enough to bury a 20-story skyscraper, dug entirely by water, right at the foot of the dam. But the mechanical battering is only the first layer of the physics. We must descend into the microscopic realm to find the true assassin. Cavitation. As the water accelerates down the spillway, the pressure within the fluid stream drops. If the pressure drops below the vapor pressure of water, the liquid literally tears apart. It boils at ambient temperature. Millions of microscopic bubbles of water vapor form within the stream. This creates a frothy, white mixture. To the naked eye, it looks like foam. To a physicist, it looks like a field of landmines. When these vapor bubbles travel into a region of higher pressure, such as the impact zone at the bottom of the dam, they collapse. They don't just pop. They implode. The vapor turns back into liquid in a nanosecond. This implosion is violent on a scale that is hard to comprehend. The surrounding water rushes in to fill the void left by the bubble, creating a microjet of water. This microjet hits the adjacent surface, whether it is concrete or rock, at speeds of up to 500 meters per second. That is faster than the speed of sound in air. The pressure at the tip of this microjet can reach gigapascals. A gigapascal is 10,000 bar. It is a stress level that exceeds the strength of any material known to man. It blasts atoms off the surface of the material. Now, imagine billions of these bubbles imploding every second against the rock foundation. It eats the material away, leaving a pitted, sponge-like surface. It weakens the rock, making it susceptible to the hydraulic jacking we discussed earlier. Cavitation turns the water into a sandblaster, stripping away the skin of the earth to expose the vulnerable veins beneath. The tragedy of scouring is that it is often invisible. The scour hole is filled with churning, opaque water. It is hidden beneath the surface. Engineers rely on bathymetric surveys, using sonar to map the bottom, to see the danger. But during a flood, when the spillway is fully open, you cannot survey. You have to wait. And while you wait, the hole grows. The geometry of the scour hole is critical. If the hole forms significantly downstream, it might create a deep pool but leave the dam safe. However, the turbulence of the plunge pool creates a reverse roller. This is a vertical vortex where the surface water flows away from the dam, but the bottom water flows back towards the dam. This reverse current drags the debris and the grinding action upstream, towards the dam's toe. This is the nightmare scenario. Regressive scouring. The hole migrates backward. It eats its way toward the foundation. Let's analyze the structural implications. A gravity dam relies on its weight, and its friction with the ground to hold back the reservoir. It transfers the immense horizontal thrust of the water into the earth through its foundation. The toe of the dam is the pivot point. It is the point of maximum compressive stress. All the forces pushing against the dam are trying to tip it over this point. If the rock supporting the toe is scoured away, the dam loses its braking mechanism. The stress distribution changes instantly. The concrete, designed to be in compression, is suddenly subjected to tension. Concrete hates tension. It is brittle. It snaps. Furthermore, as the scour hole deepens, the side walls of the valley can become unstable. We call this slope instability. The water undercuts the canyon walls that flank the dam. A landslide into the plunge pool can displace massive amounts of water, creating a tsunami that overtops the dam walls or destroys the powerhouse. But it can also remove the lateral support for the dam abutments. Let's look at the thermodynamics of this chaos. The conversion of potential energy to heat. When water falls 100 meters, its temperature rises slightly due to turbulence and friction. While the temperature change is small, fractions of a degree Celsius, the total energy dissipation is astronomical. We are talking about gigawatts of power. A large spillway releases as much energy as a nuclear power plant generates. But instead of turning a turbine to light up a city, this energy is dumped directly into a confined space of rock and water. The vibration induced by this energy dissipation travels through the ground. It can liquefy the soil. If the dam is built on anything other than solid, monolithic bedrock, the vibration alone can cause liquefaction, turning solid ground into a soup that can support no weight. The dam simply sinks. We have seen this threaten structures in the real world. The Kariba Dam, straddling the border of Zambia and Zimbabwe, faced exactly this existential threat. The plunge pool had been scoured out to a depth of 80 meters. The hole was undercutting the basalt rock foundation. The massive arch dam, holding back the largest man-made lake in the world by volume, was at risk of sliding into the pit created by its own discharge. It required a massive international engineering intervention to reshape the plunge pool and stop the regression. Had it failed, the release of 180 cubic kilometers of water would have erased civilization in the valley below, for hundreds of kilometers. The irony is palpable. We build these structures to control water, to harness it for irrigation and power. We use thousands of tons of steel and millions of cubic meters of concrete. We calculate safety factors to 2 decimal places. Yet, we essentially point a high-powered water cannon at the very feet of the giant we have built. We rely on the geology to hold up. But geology is flawed. It has hidden seams, soft pockets, and brittle faults. The water finds them all. The water always finds the weakness. It probes with the patience of a glacier and the violence of a hurricane. Let us return to the moment of failure. The scour hole has undercut the toe by 5 meters. The dam is now a cantilever, a shelf hanging over a void. The shear stress on the remaining rock is too high. The rock shears. A massive slab of the foundation snaps off and falls into the scour hole. The dam drops. It might only drop half a meter. But for a rigid concrete structure, half a meter is the end of the world. The seal with the canyon walls breaks. High-pressure water from the reservoir injects itself into the new gaps. This is the breach. The water widens the cracks instantly. The structural unity of the dam is gone. It is no longer a monolith. It is a pile of disconnected blocks. The upper sections of the dam, no longer supported, crumble forward. The roar of the collapsing concrete is lost in the roar of the escaping reservoir. The water, freed from its prison, accelerates. It picks up the debris of the dam, chunks of concrete the size of houses, and uses them as battering rams to destroy everything downstream. Bridges, towns, forests. The landscape is scoured clean. Return to the bedrock. This is the ultimate expression of entropy. The orderly, high potential state of the reservoir is converted into the disorderly, high kinetic state of the flood. The dam, a symbol of human order, becomes the instrument of chaotic destruction. Engineers fight this with energy dissipators. They build ski jump spillways that launch the water into the air, hoping to shatter the jet into a mist before it hits the riverbed. By aerating the water, mixing it with air, they reduce its density and its erosive power. Air cushions the impact. They line the plunge pools with reinforced concrete meant to withstand the bombardment. But concrete wears out. Rebar rusts. The water never stops. It is a constant battle of maintenance versus decay. Every time the spillway opens, the clock ticks faster. We scan the riverbed with sonar, looking for the shadow of the scour hole. We watch the depth gauges. We listen to the hydrophones for the sound of grinding boulders. We are trying to predict the behavior of a chaotic fluid system, interacting with a heterogeneous geological solid. It is one of the most complex physics problems on Earth. And when we get it wrong, the result is not just an error in a spreadsheet. It is a valley stripped of life. It is the erasure of history. The scouring mechanism teaches us a fundamental lesson in physics. Energy never disappears. It only changes form. We take the energy of a river and stop it. We store it. But when we release it, we must pay the price. We must dissipate that energy safely. If we don't, the energy will dissipate itself by destroying the container. The water jet that carves the scour hole is a reminder that nature is not static. We build static monuments in a dynamic world. We draw lines on maps and pour concrete into forms, expecting them to last forever. But the water is patient. The water is relentless. And given enough time and enough velocity, the water always wins. The universe is full of chaos. But we are here to decode it. Stay connected to Surphysia.